Hello everybody, I'm Savion, and today I'm going to be talking to you about continued fractions. So what is a continued fraction? A continued fraction is an object of the following form. This is an irrational number, as for all the b's and all the a's are integers, as you can see right here. And continued fractions are numbers. They're a representation of a number, and they're useful for many different things. One thing is that since they're rational, they're actually really good approximations to irrational numbers. You can use continued fractions to factor integers, and continued fractions were used in history by a lot of greats in mathematics, such as Euler, who proved that e was an irrational number, and Lambert, who proved that pi was irrational using continued fraction representations of these numbers. So this is an example of a simple continued fraction. We're mostly going to be looking at simple continued fractions today. And a simple continued fraction, you have all of the numerators are just ones, and then these a sub naught, a sub 1, a sub 2, and so on are integers. Here's an example of a continued fraction of pi. I just put this here so you can see instead of the more general form, they're just integers for all the a's. So let's start by building up a continued fraction. We're going to see where they come from, and we'll slowly build them up. A natural place to start is the Euclidean Division Theorem. And what the Euclidean Division Theorem says is that given a and q that are integers, b greater than 0, there exists unique q and r such that you can express a in this form. So I'm sure you guys have seen this before. You've probably used it many times if you've taken number theory or something. But just to refresh you guys, I'll just do an example really quick. So say you had number 11, and you wanted to divide 11 by 3. So what this says is that this is your b, this is your a. There exists a unique q. This is your q. It doesn't matter. Okay. What this says is that there exists a unique q and r such that you can express it in that form with the condition on r being the remainder that is less than b or greater or equal to 0. So what you can think, I kind of think this a little bit differently, which will help us build up the continued fraction, is that when you do this product, you have to get this product within one remainder, within one 3, within one b term of this 11. So say you chose like 2 here, and that's going to get you to 6, and you're not within 1/3 of 11. So that forces you to choose a 3 here, and your remainder is obviously going to be 2 to get you back to 11. And that condition on the remainder ensures that these are unique. And if you're really interested in this, you can read my paper and provide a proof for it. So moving on. To build up our continued fractions, what we can do is we can take that division theorem and repeatedly apply it. So instead of, I know this looks super complicated in the more general form, it's not actually that bad. We're going to take, say we're going to take 121 and we want it to be divided by 7. So we're going to do the same process once again, and we're going to multiply 7 by 17, which will give us 119, and then the appropriate remainder is 2. And then what we can do is we can just do that same process again. We can just start it again with our term here and our remainder. So we're going to have, 7. 7 is going to be expressed as 2 times, that's going to be 3, yeah, plus 1. Sorry, I'm really bad at basic arithmetic. All right, so that's going to get us to 6 and 1, and then we can do it one more time because the process hasn't terminated yet. And we're going to have 2 is equal to our remainder times, obviously, 2. So that is just me repeatedly applying the Euclidean Division Theorem. And this process is actually useful in itself. If you've taken number theory, you probably recall that this will give you a method of solving linear Diophantine equations, and also it gives you the greatest common divisor between two numbers. So that's always going to be the last non-zero remainder, the GCD of 121, and the other number 7, which we divided it by, is 1. All right. on. Oh, also I forgot to...
There's a little continued fraction in what you just did.
Yeah, we're going to get there. We're going to build it up. Patience. Alright, oh, also what I forgot to mention is that if you started with two integers, that process is always going to terminate as well. It's a pretty efficient algorithm. So now what we're going to do is we're going to take, this is the Euclidean division algorithm right there, as you just saw it in the previous 2 slides ago or whatever. And what we're going to do is we're going to divide everything by b here. So it's still exactly the same, you still have the same condition, but you're going to divide by b. And then how you find this q is going to be found in the same way that we were finding the q before, such that this is maximal, but not exceeding a over b. So, okay, I'm going to introduce you to some new notation, which will help us kind of expedite the process, which is the greatest integer notation, which is also known as the floor function. So it looks like this, and you put integer in here, and what this does is it takes the integer below it. So say you put 7.63 in here. What this says is that you're going to take 7. And when I say below, I mean on the number line. So like this is 7 point some junk, and these are integers 7 and 8. And you always take the integer right there. So I'll call this the greatest integer, or the integer part of a number. And that's basically what that q term is going to do for you. So just another example, if you actually started with an integer, it's just going to be 2. And then say you started with like negative 3.9. It's still going to be the integer below it, so it's going to be negative 4. Great. Moving on, so this is the division algorithm written out in the new form. I've just taken a over b, I've divided it, and see I wrote here for you guys that the q naught and all the rest of the q's are the greatest integer of a over b. So this still looks kind of scary, but I'm going to take an example for you guys, and it'll become really clear how you build up the continued fraction with this. But first off, I need to mention that this process can actually be generalized. With the new way that I wrote it, you can generalize it to rational numbers, but also all real numbers. And then you're going to still find the q naughts in the same way. But what's interesting is that if you began with this x such that it's an irrational number, none of the q naughts, the integer parts, are going to ever exactly be the irrational number. So this process won't terminate in the same way that it did before when you had integers. And actually, continued fraction of an irrational number will be infinite. It will continue forever. So, and then we're just going to do exactly what we did before, but we want to build a simple continued fraction. As I said, we're going to be focusing on those today. So I'm going to take the part that's left over, the fractional part, and throw it over 1. And this process will just continue, and I'm going to do an example, and you guys will see that it's actually not that bad once you get the hang of it. All right, cool. So let's build up a continued fraction of 11 sevenths, just for fun. So we're going to start off by finding the greatest integer of 11 sevenths. So, anyone want to take a guess what this is? 1? Great, you guys are listening. All right, wonderful. 1. And then what we need to do is just add the fractional part back in so that this is a true equality, which is going to be 4 sevenths.
Yeah.
Makes sense, right? Yeah. Sorry, I'm really bad at basic math. Yeah, this is true. 7 sevenths plus 4 sevenths is indeed equal to 11 sevenths. But, like I said, we want to build a simple continued fraction, so we want this numerator to be a 1, not a 4. So, equivalently, we can write it like this. So now we're on our way to building a simple continued fraction, but we want to continue this such that this is going to be an integer, not a rational number. So we're going to do the process just repeats. Start once again. Greatest integer of 1/4 is going to once again be 1, I hope. Yes. And we just keep going like this. And look, we're building a continued fraction. Isn't this fun? you just keep doing the same thing over and over again. And eventually you end up at 1/3, and you get 1/3 at the last spot here, and then you can't do the, I mean you can, but the greatest integer of 1/3 is just going to be 0. So that's how you know that your process terminates, because I can add 0, but it's not going to do anything else. So we have just built the continued fraction of 11/7. Ta-da! Okay, so now I'm just going to give you guys one more. I'm going to do 3/4, just because it'll be useful in the future. So if we start with 3/4, the greatest integer of that is going to be 0. Oh, and this continued fraction also eliminates another point, such that this first piece, this first one, can actually be 0. It can also be negative, but all of the rest past that are going to be positive integers. And then you're just going to do the same thing, continue on in the same fashion, and you arrive at this. Just leave that there, it might be useful in the future. Here's an example of a finite simple continued fraction, just so you guys can see. That one was rather long, glad I didn't choose that. And here's a more general form where you can see that these are all integers. And then here's an example of an infinite simple continued fraction, pi/4. You can see the ... which means it trails off to infinity. And here's the general form of an infinite simple continued fraction. Okay, now I just want to introduce you guys to a little bit of notation, a definition, which will just kind of speed up the process of me talking. So that's going to be that of the partial quotient. And the partial quotients are these a1, a2, a3, a4, and so on, which are integers. And also I'm going to give you guys some new notation for the continued fraction. As you can see, the continued fraction is kind of, you could say maybe like a clunky notation. It takes up a lot of space. It takes a long time to write it. So we can express continued fractions like this, using the square bracket. And then, since this first piece can be 0 or negative, it's a little bit different. We're just going to separate it off with the semicolon. And then you have the rest of your partial quotients. You just write out the partial quotients here. This continued fraction is exactly equal to this in the new notation.
For the simple ones.
Yeah, for the simple continued fractions. But we're going to be focusing today on only simple continued fractions. Great. Now we're going to talk about convergence. So if you take, for example, this continued fraction, and the partial quotients are going to go from Q1 all the way to Qn, the convergent, or a convergent of this continued fraction, it's the same one from this string to the next one, is going to be a continued fraction in which, so the previous continued fraction went up to Q sub n. This one is going to go to Q sub j such that j is less than or equal to n. So I just really want you guys to be sure on what a convergent is. So if we took a continued fraction which looked like this, say that was our continued fraction of whatever, a convergent of this continued fraction could be exactly the same thing, or it could be if we took out this step. So that is a convergent of this continued fraction. We're just going to have a few fewer steps. So if we took the first convergent of 3/4, it would be 0. And then the next convergent would be just 1. It would actually be 0 plus 1, which is exactly 1. So as you can probably assume, the longer your convergent is, the better approximation it is to the actual number, because 0 is a pretty poor approximation to 3/4. 1 is also a pretty poor approximation to 3/4, but as you go on, it gets better and better. And 1 is actually a better approximation. It's only off by 1/4 instead of 3/4. So that'll be a trend that we'll develop on in the future. This is just motivation for the next theorem. I'm going to skip it because you guys are already pretty pumped up, I can tell. All right, so this is theorem number 1. So I know this looks super crazy. It's actually not that bad. So this is just, what this means basically is that all of your convergents are defined recursively in terms of your previous convergence. And what you need is just these first 3 kind of base cases to get you started, because you can't define like convergent 1 in terms of convergent -2. That doesn't make any sense. So you start off with these to get you started, and then your convergent will be given by P over Q, which I've written out right there. So you can see that for reference when we go through this proof. Oh, and there it is too. Yeah, so your convergence will be given by this expression, and these are your partial quotients in the expression. All right, so this proof is going to be by induction, and what we're going to basically be doing through this proof to get us started with the base cases is we're going to take C naught, and that's going to be our first convergent. And what I'm going to do is I'm going to write it out. See, that's my new notation for the continued fraction, just the shorter notation. And then I'm going to actually write it as our continued fraction. And then I'm going to turn it into a ordinary fraction. So our base case, you see, we have P naught over Q naught, which is what we wanted to see. That's how it was defined previously for the first convergent. And we're going to do the same process for the next convergent. We just take this, write out the continued fraction, get a common denominator between these two, you get this, and that is exactly what you expected to see, P1 over Q1. So it's going well, and then you can trust me that I can do algebra for the third base case here. I'm just doing the same thing, that's all, not doing anything crazy. And then you do arrive at the third convergent, P2 over Q2. So that completes the base case for k equals 0, 1, and 2. And now this is going to be exactly what I have over there, my inductive hypothesis, that this is true. You have this expression defining your convergence. And then we're going to assume that we have the next convergence, the k plus 1 case. You guys have all seen induction before. And I'm going to do basically the same process, but I'm going to take a little bit of a shortcut because we already had, by the inductive hypothesis, that expression, c sub k. So I'm just going to sub in c sub k plus 1 into that, and that's what we have right here. And then I'm just going to do the same exact thing that I was doing before, some algebra, and then a lot of algebra, and then you do arrive at p sub k plus 1 over q sub k plus 1, which is exactly what you wanted to see from the proof. That's your next convergent. All right, so now I'm going to talk a little bit about the sequence of convergence, and I'm going to do that through example instead of giving you guys another theorem to prove, because it'll show you what I'm talking about, and then it is actually true that you can generalize it. So, say we're looking at the continued fraction of 3/4 here, and we're going to take the first convergent, which is 0. So, this is 3/4. Our first convergent, which is 0, is too small. So it underestimates 3/4. And that's, also q sub 0, p sub 0 over q sub 0 is an even convergent. Then our next convergent is going to be 1, which overestimates 3/4, but not as bad. See, this is 3/4, it's a little bit closer. And then our next convergent, our next even convergent, is going to be closer yet. And the next odd convergent is also going to be closer and closer. So our convergents kind of go in this pattern, and as you take them out to infinity, if you can, or just until you get to the last convergent if you're looking at a rational number in the first place, they do actually indeed converge to the number you're trying to express. And they converge in this way, such that the even convergents define a monotonically increasing sequence, and the odd convergents define a decreasing one. And that's kind of how the convergents work, and that's how they will converge on the actual number that you're trying to make with your continued fraction. Also, these convergents are pretty great. They're, as we've been talking about, continued fractions are rational numbers, and convergents are the best approximation that you can get to an irrational number with a continued fraction, which is a rational number. All right, now I'm going to show you guys that square.
The last comment you made about the best approximation, what was that again?
Oh, okay. I was just saying that the convergence of continued fractions are actually the best approximation that you can get to an irrational number with the use of a rational number, continued fractions. There's a lot more that goes on there. I'm just really skipping a lot because there's a lot that goes on there.
That's one of the nice properties.
Yeah, that's really cool about them. Yeah. Now I'm going to show you guys that the square root of 2 is irrational, and I chose this because in Math 100, probably the first proof you guys all saw when you were introduced to proof by contradiction was that the square root of 2 is irrational. And now I'm going to provide you with a much longer, more complicated direct proof, however, that the square root of 2 is irrational. Seeing how much time I've got left. Oh, I've got time. Doing great. Just for fun, I'm going to actually show you the proof by contradiction because I like it. So, by contradiction, you assume that the square root of 2 is irrational. Yeah, I know. I'll get there. But this is fun, you know. You guys like math. So you're going to assume that the square root of 2 is a rational number. Therefore, it can be expressed as a ratio of two integers. And we're also going to further assume that this a over b is fully reduced in lowest terms, such that the GCD of a and b is equal to 1. So you could basically say, another way of saying that is that a over b, a is even and b is odd, or b is even and a is odd, or they're both, it's fully reduced. So what we can do is we can square both sides. All right, and that'll get us to, and then I'm also going to multiply both sides by b squared. I know, you guys know this. I like this proof. It's cool. I understood it that day in Math 100, and that was a big day for me. So, by definition of an even number, a squared is even, so we can replace it with 2c. All right, you guys know how this is going. All right, know what I'm going to say next. Obviously, this violates one of our assumptions because we assumed that a over b was in its fully reduced form, and we have an even number and an even number, therefore it wasn't reduced. Therefore, the square root of 2 is irrational. Yeah. All right. So before we get started with our continued fraction proof that the square root of 2 is irrational, we need some definitions. We need one preliminary lemma, and then we'll go for our theorem. And then it will be really easy to determine from that the square root of 2 is irrational. Oh, we also need the continued fraction of the square root of 2. So you're going to write this out in the exact same way that we were doing before. We're going to take the greatest integer of the square root of 2. So the square root of 2 is about 1.4 or something. It's a little bit bigger than 1, so this is going to be 1. And then we're going to write this as a simple continued fraction. So I'm going to need to write this as, well, this would be the square root of 2 minus 1, but I want to write this over 1. So I'm going to write it like this. And that's exactly equivalent. This is equal to the square root of 2. And then what we want to do is rationalize this. So we're going to multiply by the conjugate correctly, hopefully, FOIL correctly. I like foiling. It's fun. Yeah, that'll be multiplying by 1. Okay, so then that's going to get us to minus 1, which is 1. Plus 1. See, we're on our way. Got our first step there. And then just for the sake of time, I'm going to go ahead and just write the rest of it out. Continue on. So we need this definition, that of periodic continued fractions. A simple infinite continued fraction is periodic if there exist natural numbers n and k, such that an equals an plus k for all n, such that n is greater or equal to n. So what this means, that might sound kind of complicated, it's actually not that bad. It just means that if you're writing out a continued fraction, I'm going to use our new notation here, and I'm just going to make up something. It means that at some point the continued fraction starts repeating. So we have 3 and the 7 that just repeat on and on and on. That's what a periodic continued fraction is. And we can denote that with this overline here, which means the same thing that it always has, and that part repeats. All right, and now we need the definition of what a quadratic irrationality is. we say that alpha is a quadratic irrationality if alpha is an irrational root of a quadratic polynomial with integer coefficients. So that's right there. We just have this polynomial with integer coefficients, and we have alpha is a root of that, which means that if you put alpha into this polynomial, you get 0. Here's an example, 1 plus the square root of 3, and that's your polynomial. If you put that in there, you get 0. You guys can trust me on my math there, or you might not, but whatever. You do get 0. And also the square root of 2 is one such number. Isn't that cool? It's like the matrix. You guys like that? Okay, so next we need one last definition, and I put the quotes over it because it's not really a definition, it's a theorem. I should prove it to you guys, but I'm kind of running out of time so you guys can trust me. So the real number alpha is a quadratic irrationality if and only if there are integers a, b, c, and b greater than 0, c not 0, such that b is not a perfect square. Basically, if you can express alpha like this, it's a quadratic irrationality. All right, now we need a limit. Well, I'm really running out of time. So you guys can trust me that this is true. What this means, though, what's important to get from this lemma is that if you take alpha, which is your quadratic irrationality, and you multiply it by an integer, you add an integer to it, or if you divide it by an integer, add another integer to that, it's still a quadratic irrationality. That's the point of this lemma. And that'll be useful in our proof that we're going to need coming up here.
Or rational.
Or rational, yeah. We're going to ignore that part. No, really, that actually would become clear in the proof, but we're only interested in the quadratic irrationality side of that. So I'm sorry, but I'm going to skip this proof. I did do it. See the square? That means I did it. All right, so now we're going to have theorem. My first one was named Theorem 1, and this one's Theorem. Okay, that's odd. So this is the one that we're going to talk about right now. The infinite simple continued fraction of an irrational number is periodic if and only if the number is a quadratic irrationality. And that will allow us to get, from our continued fraction of the square root of 2, we'll be allowed to conclude that the square root of 2 is a quadratic irrationality, and therefore irrational. And that's what we want to get. So this is an if and only if statement, but I'm only going to prove it in the forward direction, which will get us what we want of looking at the continued fraction and then getting the information we want out of it. So what we're going to do is we're going to begin with alpha, which is a continued fraction, and we're going to assume that we have a periodic simple continued fraction. So I can write it like this with the overline, and all that means is that from a sub big N on, that this piece continues. It repeats in the continued fraction. Now, what I'm going to do is I'm going to call beta the repeating part of the continued fraction. So beta is equal to this, as you can see there. And that will allow us to write beta like this. This is the continued part. And then after the continued part, it will repeat again, so I can put another beta in there. And that allows me to remove the overline notation. So by Theorem 1, which was the theorem which defined our convergence, and I still have it written out over there, we can write beta in that form right there. And then what I'm going to do is I'm going to take that convergent, and I'm just going to clear the denominator by multiplying both sides by the denominator, which will get us this. And then I'm going to just distribute in the beta, and over there I'm going to FOIL again. And you can trust that I've done this correctly. You'll arrive at that, and I'm going to take everything from the right-hand side of that equation and subtract it over to the left-hand side, and that will give us this. And if you look at this, this might look familiar. You may have seen this just a few slides ago. Beta is satisfying this polynomial, this quadratic polynomial. So beta is a root of it. Therefore, beta is a quadratic irrationality. So you put in beta, and you get that it's equal to 0, and it fits the correct form. Now, we're going to take a step back. We're going to go to our alpha. This is the original periodic continued fraction that we started with. And what I've done is I've just put beta in here. So it's the repeating part. Same exact thing you just saw a minute ago, except it doesn't have the overline. And then we're going to use that same theorem on the convergence, which I still have over there, to write out alpha. And we've got beta. So what this gets us is, wait, we're not ready for that. We have the convergent of alpha written out here. But then if you look at this, you've got beta, which we just proved was a quadratic irrationality, multiplied by an integer, added by an integer, divided by integers. And by our lemma, beta is still a quadratic irrationality. And since the right-hand side is a quadratic irrationality, which is equal to the left-hand side, we can conclude that alpha is indeed a quadratic irrationality. Square. All right, so now we can take this theorem and we can apply the square root of 2 to this and observe that the square root of 2 is a periodic continued fraction, an infinite periodic continued fraction. And because it fits the form, we just run it through the theorem, and the theorem says, therefore the square root of 2 is a quadratic irrationality. And I mean, yeah, that's what I mean. It's an irrational number. So there we go. All right. Thank you guys very much for listening to my presentation.